Welcome everyone, I'm Jim Corkins, and we are now going to be doing 2.2 electric fields in 2D. Alright, so if you haven't done the reading, please do the reading. It will help you out immensely. So please read OpenStax or Survey or both of them because they both have different perspectives. Alright, well, let's go ahead and get started. And this is also an tutorial example, so it's both. Okay. Now the first page of your tutorial, it's about estimating the size and direction of electric field vectors, and then creating a net electric field vector. Okay. So we'll talk about it, but So suppose we have a negative Q here, a positive Q here, and negative Q here. And let's take a look at this negative Q here. So I'm gonna make some colors here. So this will be a positive Q, and we'll call it red. This will be a blue negative Q, and we'll have a purple negative Q. All right. So starting with this negative Q, it's going to have a large electric field pointed up and towards it. And pointed towards it. And you're just drawing the electric field vectors. You don't have to label them in this one. This positive charge is creating an additional electric field that is in the same direction. Okay. And it'll be the same size too, because it's the same distance and same magnitude. And now we have a purple negative Q that is going to have an electric field pointed down towards it, and it'll be smaller. Okay. Now, what we're supposed to do to create the net electric field vector is add vectors in 2 dimensions. Okay, so just like that tutorial back when I had you review in week number 2. So if you're having a hard time doing vector addition 2 dimensions, please check out that optional review about addition of vectors in 2 dimensions. So it doesn't matter the order in which you do this. I'm going to do this off to the side over here. I'm going to have the negative vector pointing up. I'm going to do my best to make sure I have the sizes of these vectors the same as this. And then we're going to add the red to it. And then we're going to add the purple one, which looks like it's smaller. So this is about the electric field, the overall electric field vector. Okay, so you started right here, you walked up and to the left, and then down and to the left, a small amount. So you go from start to the finish of your trip. Right, here's the finish. So that vector, that overall net electric field vector, is going to be large, and it's about this size, and it's going to be pointing up and to the left. Okay? So this is the basics of how you do this. So I'm going to go ahead and label this the net electric field with a little summation of A. And I'm going to write EA over here. So when you're watching this again, you'll know which ones correspond to which. All right, let's do B. The red electric field is going to be smaller and pointed away from it. The blue electric field is going to be smaller and pointed towards it. These don't have to be perfect. And the purple electric field, this looks like they're all the same distance, is going to be smaller and pointed towards it. So off to the side over here, I'm going to do addition of vectors. Just because I'm on purple, I'm going to start with that one. Going to go down and to the right. And then let's do B. Straight over to left. Oops. So all these vectors should be the same size. And then blue is going to be up and to the right. Okay. I don't know if I trust that one. I'm going to try this again. Yeah, I'm going to try this again. Let's try this again. I don't know if I trust that. What am I saying? I don't know. I definitely don't trust it. I should have had more of an angle to it. That purple one. And the red one should be the same size vector. And then blue should be pointed up and to the right. It should, yeah, that's about right. So if you look at this, it's starting and stopping at the same place. So this guy, which is the net electric field due to B, is going to be 0. I guess I do trust it. There we go. So since it's starting and ending at the same place, this guy's electric field is going to be equal to 0. All right, let's do C. I'm going to do C over here. Well, I'm going to do it right on here first. So the blue guy's electric field vector is going to be a little bit larger than this guy and pointed up. The red guy's electric field vector should be a little bit even larger than the blue guy's and pointed to the right. And the purple guy should be the same size as the blue guy and pointed straight down towards it. So when we add those vectors together, starting with purple, actually let's start with red this time. That electric field vector is pointing to the right. Then we have an electric field vector down, and I just grabbed whatever works. And then, in a way, we're kind of doing addition of vectors in 1D right here with the blue and the purple. It goes back up to where it started. So you started right here, you ended right here. Walk to the right, down, up. So this guy's net electric field vector is just going to be pointed to the right. Okay? And so this guy's net electric field vector is basically just the red guy. So and I'll do it right up here. All right, the purple, so let's do D. That negative blue charge is really far away, so this is going to be a small vector. We're really close to that positive charge, so that electric field vector is going to be pointed towards it, away from it. And the purple guy is the same distance and same magnitude, so it'll be like this. So we'll do D over here, starting with let's start with the blue guy this time. Blue guy is a little guy. He's just pointing up and to the left. There you go. Next comes a purple. Down and to the right, down and to the left. And then red. It's going to add to that. Down and to the left. So the overall vector, you started here and you ended here. So this is going to be the overall vector. So drawing that right there. So this is going to be the electric field vector due to D, the overall electric field vector. This is ED. Okay? So this is how you do it, and this is good practice because what this does is it gets you to estimate the sizes of those vectors in those directions, and you're really practicing the main concepts of electric fields here. So without using numbers. You have to be able to do this qualitatively as well as quantitatively. All right? Now, for the quantitative part of this, we're going to go ahead and come over to here. So this tutorial should look familiar because we've kind of done it before. But let's go ahead and do this now. So this is 2 dimensions electric fields vectors. All right. So you have a positive 2q is creating an electric field at this point P. That's where our sensor is. Now that positive 2q's electric field is going to be pointed away from it. And that's going to be the electric field due to that positive 2q. And we don't know the distance it is. So we need to figure that out. Well, this is that distance right here. And so I'm going to make it a dotted line, and so we can number this. All right. Well, to get this distance right here, that's c squared equals a squared plus b squared. So c squared is going to be equal to l squared plus 3l that we're going to square. So that's going to be, what is that? 9, so that's going to be 10l squared. So c is going to be equal to l square root of 10. Okay? So this distance is L square root of 10. All right. Now that we have that, let's make our triangle. So I'm going to use this as my triangle. That vector is pointing down and to the right. So I have a right vector, a down vector. So here's my triangle. I'm going to call this theta, and that means this is the concentric triangle over here. So to get what that theta is, so we're going to have tangent of theta. That's going to be equal to opposite over adjacent, L over 3L, which is 1/3, because those L's cancel out. So tangent of theta is going to be equal to 1/3. So the inverse tangent of 1/3 is going to be equal to, and I don't know what that is, 1 divided by 3, trigonometry, second function, tangent, 18.43. So this is going to be 18.43. So now I'm going to replace those thetas with 18.43. Okay. Oops. You know what I forgot? Slipping up here. I should have laid down my coordinate system. Positive x, positive y, negative x, and negative y. See, when I lay down that coordinate system, how much more clear it starts to look? So that's why you're supposed to start from the beginning with the coordinate system, because it really does help you out. All right, this rightward vector is pointed to the right, and that's going to be our hypotenuse, which is positive 2q, comma, L square root of 10 cosine of 18.43. The other side is going to be the same hypotenuse, but it's pointing down, positive 2q, L square root of 10 sine of 18.43. And what I'm going to do is just grab this and maybe scooch it down here. That way you have a little bit of room I could work with. So our angle, which this, you don't, I just, again, our angles are either going to be 18.43, or if you use this as your triangle, actually, this is your triangle here, which would be this. That would be 90 minus 18.43. $71.57. So your answers can be either one, either 18.43 or 71.57, right? All right. Continuing on, we're going to be summing the electric field in the x direction, which this is the electric field in the x direction. So that's going to be a positive, and that's going to be K times a positive 2Q all over L square root of 10 squared, which is cosine of 18.43. So this is going to end up, and I'm going to scooch that over a little bit. It's going to be, so the positive comes first, and this is going to be 2 over square root of 10 squared, which is going to be 2/10, which is going to be 1/5 KQ over L squared cosine of 18.43. So this is going to end up becoming, and I'm going to write a number, and we're going to, we want to round to the 100th. Okay, so let's go ahead and do that here. So whatever the cosine of 18.43 is, and it's going to be divided that by 5. So 0.189. So that's going to be 0.19. So that's going to be positive 0.19 KQ over L squared. So that's going to be positive, positive 0.19. All right. Let's go ahead and sum the electric field in the y direction. Now, you can skip steps. It's going to be the same hypotenuse, right? Except this guy's pointing down. So looking at this, we have a downward pointed, and it's going to work out to be the same thing, but I'm going to look at this when I'm looking solely at this when I'm constructing it, over L square root of 10 squared, and that's going to be the sine of 18.43. 3. So this, we already know, is 1/5. So we know the answer here is going to be, it's going to be pointing down though, -1/5 KQ over L squared sine of 18.43. Okay. So 18.43 second function sine divided by 5 equals 0.06. So this guy is going to be equal to -0.06 KQ over L squared. And that is your answer. Okay. So very similar to what we did before in forces. And we're rounding to the 100th. So I'll make sure I put that note in your tutorials. Okay. So there is your first example. All right, let's go ahead and move on. Here we go. We've got another tutorial. Similar idea. We're going to go ahead and start off with our coordinate system. As we should have last time. Label it. Okay. So it looks like we have a -1Q creating an electric field towards it. You know what? I'm going to move this out of the way and just draw this here. And that's going to be an electric field that's negative. It's a -1Q. And it's distance 3L away. So that's where our sensor is. This positive 2Q, which we've just done this tutorial, but we're doing it again. Okay, it's pointing directly away from that positive 2Q. And we don't know the distance. So just like the last tutorial, we got to figure that distance out. And yes, I know I'm doing everything from scratch again. All right. So we found out that this distance is going to be L square root of 10. Again, it's going to be C is going to be equal to L squared plus 3L squared, square rooted, which got us L square root of 10. And that's L square root of 10. And we're going to be using this as our theta, which is 18.43. But again, tangent of theta is going to be equal to opposite over adjacent. Realistically, we could use sine, cosine, or tangent. I'm just used to doing tangent. So theta is going to be equal to the inverse tangent of 1/3, which is 18.43. Okay, so replace these guys and replace this guy. And now we have this, which I'm going to just There we go. All right. Now, same thing as last time. Got to break that hypotenuse into up and down and left and right, where this is going to be positive 2q, comma, L square root of 10 cosine of 18.43. This part here is going to be negative positive 2q, comma, L square root of 10 L square root of 10 sine of 18.43. Okay. Sum the electric field in the x direction. You always sum it. The direction will do the subtraction for you. Okay. So starting with the red guy, it's pointed to the right. E. So I'm just going to go right towards it. That's k times positive 2q all over L square root of 10 that we're squaring, cosine of 18.43, and we're going to be subtracting that from this, which is going to be k times a negative 1q all over 3L that we're squaring. Okay. And just like earlier, I know I'm going to run out of room. I'm going to scooch this over. And just like the last part right over here, we know that this k positive 2q L square root of 10 squared times cosine of 18.43, we know that that is 0.19 kq over L squared. So I'm going to just write that here for the sake of honoring your time. 0.19 kq over L squared. And this is going to be minus, that k looks weird. I'm going to take care of it right here. And this is minus 1/9. So 1/9, 1 divided by 9, 0.111. So that's 1 over 9L squared, which is 0.11 kq over L squared. So summing the electric field in the x direction, that is going to end up being positive 0.08 kq over L squared, right? So positive 0.08. Okay. In the y direction, we're going to get the exact same thing as we did last time, right? Okay, nothing changed as far as the y direction. Okay, so that was just negative k positive 2q over L square root of 10 squared sine of 18.43. So we get the same part right here. We get the same part right here, 1/5, except we're, instead of dealing with cosine of 18.43, we have sine of 18.43 divided by 5. So this is going to be negative 0.06. So that is the second page of your examples. Let's finish our final page here. Okay. So again, the procedure is you lay down a coordinate system. Oops, wow, that got a little crazy. Let's lay down that coordinate system. And label it. Positive y, negative x, negative y. The coordinate system really does help you with your triangles and your angles and things like that. It's valuable. This positive q is going to create an electric field pointed away from it at point P. So it's going to be negative. It's due to a positive 1q, and it's a distance 2d away. This negative 1q is going to have an electric field pointed up towards it. And we don't know the distance. So let's figure that out. Well, this distance right here, and I'm going to just overlay this right here. Well, that's going to be c, which is going to be equal to d squared plus 2d that we're going to be squaring. So that's going to be equal to, it says 4, 5. So that's going to be, oh, and then we're going to have to square root it. So let's make this so it's, you could read it, plus 2d that we're squaring. So c is going to be equal to 2d, so that's 4, so that's going to be d square root of 5, right? You got 5d squared square rooted. I'm just taking the d to the front. So this is going to be d square root of 5. Now let's use this as our angle theta. Okay? Well, if this is theta, tangent of theta is going to be equal to d over 2d, which is 1/2. So the inverse tangent of 1/2, that's going to be equal to 0.5. Second function inverse tangent 26.57. So 26.57. So I'm going to write that over here, 26.57. Now in this problem, I don't recommend using an alternate angle, but it is conceivable that you can do that. Minus 90, 63.43. So use one of those two angles, likely 26.57. So let's go ahead and replace that with 26.57. And while I'm here, I'm going to make this guy a little bit longer. All right, which means this angle upwards, that vector upwards, and this vector to the right. I'm going to get rid of this positive y. And this is at 26.57 as our angle. Okay. Now to write this, I'm going to give myself a lot of room, hopefully. It's going to be pointed upwards, and it's going to be the electric field due to the negative 1q, comma, d square root of 5 cosine of 26.57. This side is going to be pointed to the right, and it's going to be the same hypotenuse, but it'll be the sine of 26.57. Okay. So let's sum up the electric field in the x direction, which is this guy right here. Just one. It's going to be k times a negative 1q all over d square root of 5 that I'm squaring sine of 26.57. Okay. So this is basically just positive 1/5 kq over d squared, and that should be d squared, yeah, d squared and d squared. Sorry about that. So, and then we got cosine, oh, nope, sine of 26.57. So the electric field in the x direction, that is going to be just be equal to positive, and let's go ahead and do it, 26.57 second function sine. We're going to divide that by 5 equals 0.089, so 0.09. kq over d squared. So positive 0.09. Okay. Now let's do the electric field in the y direction. Which we are going to have everything the same as this top one. So negative 1q d square root of 5 but it'll be the cosine of 26.57 because it's touching that actual angle. It's pointing upwards. Now we're going to be subtracting from that the positive 1q over 2d that we're squaring. So we're going to get a positive 1/5 kq over d squared cosine of 26.57, but this is going to be minus 1 over 2d squared, so that's going to be 1/4 kq over d squared. So the electric field in the y direction, it's going to be cosine 26.57 divided by 5 minus a fourth. So 26.57, take the cosine of that, divided by 5 equals, now we're going to subtract off 0.25 equals negative 0.0711, so negative 0.07. KQ over D squared. And so this is the third page of that examples. All right. So hopefully this has helped you out. All 4 of these pages will help you, give you enough tools to do your version of that tutorial. Okay, thank you. Have a great day.